The substitution method is a very powerful tool for your integration toolbox, and it allows us to substitute for more complex things and make them simpler so that we can integrate them, functions we would not otherwise be able to integrate.
So how would you analytically integrate this function? X squared plus 1, the quantity squared, times 2x dx. Well, the answer is you don't have any rules of integration to handle this. It's just a little bit too complicated. But we're going to look at patterns in here and find a way to analytically integrate it. And that's going to involve looking for a pattern of a function and its derivative using the chain rule in reverse. And we're going to call this integration via substitution. It's a form of analytic integration when our basic rules for integration do not work. And it's a technique for handling those more complicated functions like composite functions. And it is very similar. What we're going to do here with substitution is using the derivative chain rule in reverse. And this can be done really in two ways. One via what's called pattern recognition, and another a more formal substitution process. Both wind up with the same result. And the pattern we're looking for, if we can see in the integrand, the function and its derivative, or some form of its derivative, both there, then we know we can integrate it by substitution. Going back to the previous question, we know from the chain rule that here's a function, x squared plus 1. If we looked at that as a smaller part of a composite function, the derivative of x squared plus 1 is 2x. So in fact, what we have is a function and its derivative. A function is part of a bigger composite function. So this function that you see here could be integrated using the technique of substitution. So the key to this anti-differentiation of these composite functions that are a little bit more complicated, is to look for inside the composite function, if the composite function is f of g of x, and inside that we recognize some function g of x that has a derivative g prime of x that's also within the integrand, then we can indeed integrate this. And what we're going to get, when we take the antiderivative, we're going to get capital F of g of x, which is the integral of f of g of x, plus a constant, of course. And what we're going to do with substitution is we're going to so if we let u equal g of x, that allows us to rewrite this as this composite function as a simpler function f of u. If we let u be equal to g of x, then we took the derivative of that. Du would be equal to g prime of x dx. So therefore, we could write the integral of f of u du equals capital F of u, the antiderivative of f of u, plus c. This u substitution allows us to take a more complicated situation here with a composite function and simplify it by making a substitution. Pattern recognition is the process of kind of looking for that small part within the composite function that has its derivative outside within the integrand. So if we look at an example like this, 2x times the quantity x squared plus 1 to the 4th power, and we looked inside the parentheses there, we'd see x squared plus 1, and we recognize its derivative, 2x, right there. And in fact, that g of x, that thing we're going to substitute and let equal to u in substitution, is often within parentheses or radicals if we're going to do it this way. And you really just need the right power of x and g prime of x for this to work. Let's look at some other examples and see if you can find the patterns. Here inside the radical, we're going to let g of x be x to the 3rd plus 1 because the derivative of that is 3x squared. Now it's not perfect, but it's the right power of x, and that's all we really need to make this work. We'll deal with the constant difference later. Same thing here. X squared plus 1, the derivative of it is 2x, and we do have x to the 1st here, so this will also work. Again, we will deal with the constant later. Here's another example, 3x squared times the quantity x to the 3rd plus 1 to the 1/2 power. We're going to let g of x be this part right here. The derivative of x to the 3rd plus 1 is 3x squared. We look in parentheses here, if we let g of x be tan x plus 3, the derivative of tan x plus 3 is secant squared x. So this is going to work very nicely. So let's go back to our original example. The integral of x squared plus 1, the quantity squared, times 2x dx. So hopefully, using pattern recognition, you recognize here's the function g of x that's part of a composite function where this whole thing is squared. But the derivative of x squared plus 1, the derivative of g of x, is going to be 2x. So this is going to work out very nicely. Now, we're going to use formal substitution methods here. But in this case, you could also just use pattern recognition and integrate this almost immediately. So hopefully you recognize we're going to use x squared plus 1 as our u, our g of x. And so that means u is equal to x squared plus 1. Well, if we took the derivative of that, du is equal to 2x times dx. So when we rewrite this in terms of u, it becomes the integral of u squared du. And that's because we let x squared plus 1 be equal to u. So that's our g of x. We square it, because that inside of the parentheses part is squared, and we multiply it by 2x dx, which in fact we find is du. So this really complicated function simplifies down to something we can definitely integrate in terms of u squared du. And that in fact is equal to u to the third over 3 plus c, but we do need to go back and resubstitute x back in for u. And when we substitute that back in, we get the quantity x squared plus 1 to the third power over 3 plus c. And that, in fact, is our answer. And if we were to take the derivative of that, we'd have to use the chain rule. We'd get 3 times the quantity x squared plus 1 to the second power, all over 3, times the derivative of what's inside, which is 2x. And the 3's would cancel each other out, and we get the original integrand. So this is a pretty powerful way to use a substitution to integrate a very complex function. Now, using pattern recognition, because the derivative of the thing we're substituting winds up being perfectly matched here, you could actually integrate this using pattern recognition almost immediately. Because you could say, okay, I'm going to substitute here. I see a function, x squared plus 1, and its derivative. And that function is to the second power, so it's the integral of the thing to the third power over 3 plus c, and you have your answer in one step. So you can either use pattern recognition and do it that way, or you can use the formal process of u substitution, where we're letting u equal to x squared plus 1, taking the derivative, making sure it matches up, and continuing with that process. Let's kind of pull this together as a process. If we're using integration by substitution, whether it's the formal method, where you go through all the steps, or it's pattern recognition where you see it and you just integrate it immediately, both use the same basic process. So you first choose a substitution, u equals g of x. Now usually the g of x will be in parentheses or radicals, and outside that you will see a derivative. And so the derivative of u is going to be g prime of x dx. So both the g of x and the g prime of x dx need to be in the integrand originally. And then rewrite the integral in terms of u, so that it becomes a simpler function that you have analytic rules to deal with. Find the resulting integral, and then go back and resubstitute x back in place of u. That will give you the antiderivative in terms of x. And as with all integration problems, analytically, you can check your answer by differentiating. Okay, 8 minutes in, we're already well overdue for our joke of the day. And hopefully you notice they forgot the plus c. So let's do an example here. Integral of x squared times the quantity x to the third plus 1 raised to the 1/2 power. What's our g of x? What's our substitution going to be? Well, x to the third plus 1 is in the radical, and I know the derivative of that's going to be 3x squared, and here's an x squared dx term out here on the outside. So I've got the building blocks for what I need to use the substitution method. So I'm going to let u be g of x, and that's going to be x to the third plus 1, because I know when I take d, I'm going to get 3x squared dx. So the g of x, I can rewrite this as the integral of some function of g of x times g prime of x. Now that 3 isn't there, and we're going to have to account for that here in a second. And the way we're going to get that squared away is by trying to get x squared dx, because those are the two terms we see here, by itself. And I'm going to do that by dividing both sides by 3. So now I've got du over 3 equals x squared dx, and now I can do a perfect substitution because I have the integral of u to the 1/2 power times the derivative of u. So when we do the substitutions here, we put in u for x to the third power plus 1, so this becomes the integral of the square root of u times the derivative of u, which is x squared dx, times a third. That's where the 1/3 du is, because the 1/3 du replaces the x squared dx term. That and that are the same, just like u and x to the third power plus 1 are the same. When we make those two substitutions, we get this into a form we can definitely solve, because using the constant multiple rule, we're going to move that 1/3 out to the front, and when we integrate that, we get 1/3 times u to the 3/2 power over 3/2 plus c. That's going to simplify down a little bit. And so when we simplify this and we do our substitution of x to the third plus 1 for u, we get our final answer of 2/9 times the quantity x to the third plus 1 raised to the 3/2 power plus c. And in fact, if you take the derivative of that, and we did this right, you're going to get the original integrand. So you learned about the substitution method of analytic integration, which allows us to tackle more complicated functions that are composites of smaller functions.